Hi there, welcome to my presentation. This is a short presentation on weather prediction using machine learning techniques. I am Gautam Radhakrishnan Ajit, working for a fictional non-profit organization called Climate Winds. So, coming to the objective, to combat climate change in Europe, Climate Winds wants to study and analyze historical data to identify any unusual patterns, weather patterns that exist or are at the risk of existing over the next decade, and also to determine the safest places in Europe. We are working with a dataset with values from the 1800s to 2022. Apart from the meteorological dataset that is already provided, this the scope of this project could be further expanded by looking into images captured by Earth orbiting satellites, real-time sensor data installed in remote locations to identify localized patterns, geographic data, which would help analyze the terrain, elevation, land cover, etc., and the socio-political data, which accounts for any harmful biases in terms of data collection and public disclosure, since governments may have their own privacy laws or agenda in sharing data. For instance, the tourism industry might withhold adverse climate conditions to not scare away tourists. So, this is a brief summary on three thought experiments, which will be discussed further in the coming slides. So, the first thought experiment is filtering out redundant features using a random forest model and guiding human experts to focus and perhaps discover hidden relationships among the important features that contribute to extreme weather. The second thought experiment uses CNN in conjunction with other models such as RNNs or LSTMs to study how cloud patterns change over time, thus aiding short-term prediction. And the third and final experiment is about filling in the gaps in training data with synthetic data generated by generative adversarial network models. So the first thought experiment deals with variable importance, and this is where random forest models come into picture. Since we would most likely train on millions of observations when the models are scaled, it is crucial to keep the training costs low without compromising the efficiency. By training random forest models exclusively on data specific to extreme weather conditions, we would be able to narrow down the list of features to its most important ones, helping us get rid of redundant features and make training faster. This would also help human experts focus on the most important features and discover relationships between such features, if they exist. So, this is an experiment which was run on a random forest model. So, there were 15 weather stations, and these weather stations, and the graph on the left shows the weather stations ranked in terms of their importance. And among the top three weather stations identified, which includes Dusseldorf, Maastricht, and Madrid, temperature, radiation, sunshine, and precipitation all rank high, and these had the most importance. Now, coming to the second thought experiment, using CNNs and RNNs together to study how cloud patterns emerge over time. Since CNNs excel at image data, they can be used to track cloud movements and identify emerging patterns, potentially saving lives from disasters, cyclones, tsunamis, and similar events. Data can be collected from social media accounts, for instance, images on Instagram, along with their location, and make short-term predictions as to whether that place is safe for travel, bringing us back to the objective of the project, one of the objectives. The idea mentioned above could be taken a step further by feeding the spatial features extracted by the CNN layers through its hidden layers to a model more capable of studying patterns over time, like an RNN or an LSTM model. We can even use these models for forecasting the weather conditions by hours, days, or months. This is another result of an experiment run on a CNN model. So on a trained CNN model, whether there were two labels, whether the weather was pleasant or not, and the pleasantness of the weather was correctly classified for most of these 15 stations, which brought an overall accuracy of 82.76% And on the right side, we can see the set of optimized hyperparameters, which brought out the best out of these models. Now, coming to the third thought experiment, is the use of generative adversarial networks and radar recognition. With respect to the second thought experiment that we just discussed, RNNs can capture temporal patterns, but often there could be gaps in the data. For instance, maybe an hour's data might be completely missing in the training set. So in order to fill these gaps, GANs could come in handy as the generative component could create synthetic images that resemble the missing weather condition. This would in turn make the training of the existing models, the CNN plus RNN models in the second thought experiment, much stronger, and the final output would be much closer to the real world. Such situations or weather conditions which could be missing could be diverse, ranging from the formation of cyclones to the intensity of forest fires. This is the confusion matrix. So there were four weather conditions: cloudy, rain, shine, and sunrise. So the GAN was able to predict most of them correctly. So as you can see, the true values are on the diagonal. There, there were some cases where the actual weather was cloudy and GAN classified it as shine. But apart from this misclassification, most of the values are accurate. And we achieved a training accuracy of 84.93% and a validation accuracy of 81.69%. So these values are very close to each other, and therefore it is less likely that the model is overfitting and could generalize well on our unseen data. Coming to recommendations, so in line with the objective of this project, which boils down to making accurate short-term predictions, models such as CNN and RNN that could capture the spatial and temporal patterns come highly recommended. However, as discussed in the previous slide, there could be time gaps in training data, and in order to fill those gaps in time, GANs might come in handy and could act as a supplement to the training stages of the above model. Next steps is to gain accessibility to a diverse set of data, which was discussed in one of the earlier slides, such as geographic data, satellite image data, real-time sensor data, could all help widen the scope of this project. We could also explore GAN models and how they could be useful in terms of for audio data. For instance, whether we could predict the sound of thunder and rain and how that relates to the weather conditions. Thank you for listening.